Put it on a hot plate, right? Right? What happened to the water inside the can? First of all, when it was on the hot plate, got hot. So what happened to the liquid water when it got hot? Boiled and became what? Water vapor is correct. Called gaseous water. The gaseous particles were bouncing around, and because of their incredible energy, they were moving out of the can. We couldn't see them. But what did we see above the can? Steam. And that steam was little droplets of liquid water. Little droplets of liquid water. Those little droplets of liquid water are what we could see, and that's why we knew the inside of the can was hot. And most of it had become a gas. Then we took the can and flipped it over. And we flipped it over into what? Ice water. Very good. There's my ice. There's my water. Okay? Now, since it was ice water, there was gas inside of here. What did the gas do when it came in contact with the ice water? Well, it could have gone out of the can. But when you take a gas and you cool a gas, does it get bigger or smaller? Smaller. And if the gas goes from a gas phase to a liquid phase, does it get a lot smaller? Yep, about 1,000 times smaller. So that 1,000 times smaller caused the gas to condense into liquid droplets. And was there as much gas inside the can? No, less gas inside the can. If there's less molecules of gas inside the can, what happens to the pressure inside the can? Goes way down. The pressure outside the can is the same the whole time, and since the pressure goes down inside the can, and we sealed it with the water right there, we sealed it, this caused the can to get crushed.
So if you put like really cold water into the can and dunk it in like warm water, would it explode?
Technically, you could get it to explode if you could seal this. What would really happen is if you had cold water and put it into warm water, how hot would you have to have it? It could explode if you could seal that. That'd be the hardest thing to do, but yes, you could do that. And so that's what you do. That's what some people do with really cold things like dry ice. Put it into a container and you seal the top of it. It explodes. Same principle. Pressure inside is greater than the pressure outside. Yes, sir. Yes, you may. Now, the interesting thing about this demonstration is this is a very classic demonstration because this has actually happened in real life. There was a person who worked for a steam cleaner company, and the steam cleaner company had these big, huge trucks. These were called tanker trucks. Okay? And in a tanker truck, it was a cylindrical container, and the person went in to clean the container. Okay, kind of like a gas truck. So imagine a gas truck in your head. Gasoline, one of the ones that delivers it to like Costco or some other place. Okay, the person walked into it and he cleaned out the entire inside of it with a steam cleaner, which was a high temperature liquid and gas mixture. So he heated it up during the day. He went home from work at 5 o'clock in the evening and he put the cap of it, he didn't leave it open, but he closed the cap. He sealed it because it's a sealable container and it was really hot. Then at night the temperature dropped really low. And what happened is it was really hot in here, the hot gas. The low temperature caused the hot gas to condense into liquid water. And when it condensed into liquid water, what happened to the tanker? It got crushed. The pressure due to the atmosphere crushed the pressure inside because it was much greater, and the tanker looked like this. I do, but I'll have to show you later because I don't have it on my display anymore. Okay? And you had a little cap thing still placed on there. So, this can happen with a small can or a very large can, like a container. The next one was our submerged cup. So now that we know a little bit about what happens with pressure, how did the submerged cup keep our stuff dry? So the cup's underwater, completely underwater. Why didn't the paper get wet?
Air pressure.
Air pressure, where's the pressure?
Air pressure is inside the cup.
There's air pressure inside the cup. Pressure inside the cup due to the air. The water level went up a little bit because of the water pressure. The atmospheric pressure is pushing down on the water, but it does not go up into the cup because of this air is pushing down with the same force that the water is pushing up with. The air pressure mat. Why was it hard to pull up the air pressure mat? Because you've got air pressure pushing down on it. And the thing is, when you try to pull it up, the pressure is pushing down. The amount of force it's pushing down with is 14.7 pounds per square inch. So if you imagine on your head, if you have a small head, maybe your head was only an inch big, you'd have 14.7 pounds pushing down your head right now. For those of you with big heads, you have more pounds pushing down on top of your head right now. It's actually pushing all over on you, but pushing down on your head is one way to visualize that. A little square about that big, straight up in the atmosphere is pushing down on you. This is one reason why we can't jump as high as we normally could. Kevin, put it down. All right. This is also why it's much easier if you pull up the side of it, because it bounces out the pressure. Does not have the same amount of pressure pushing down. So let's try to explain what happened with the cup and the card. Here's our cup. Here's our card. Why didn't the water fall out of the cup? There's no sucking going on. Thank you. Sorry. When you talk about pressure and you talk about vacuums, there is no sucking. Your vacuum at home does not suck. Just want to tell you that. It doesn't suck. Okay? It creates a change in pressure. So the vacuum at home, it's got a tube or whatever. Okay? It creates a change in pressure. The pressure inside is less than the pressure outside, so the air goes in. That's why it moves the air. It has nothing to do with it sucking. Okay? Even though vacuum companies will tell you differently. So here we have water. So the air does not suck the water up. What causes this card to stay in place? Not sucking. Pressure of the air. What air? There's air trapped in the cup. There's also air where?
Around the cup.
Around the cup.
Below the cup.
It's pushing up. This is pushing down. The pressures are equal to each other. That's why the cup and the card do not move. If you squeeze the cup, which exerts more pressure, when you go, whoop, squeeze it, the whole thing explodes. That's how you can do this demo and pretend to be really good at it and make water go over someone's head. So if I had a volunteer, like if Kevin wanted to volunteer and I could be like, oh, I don't want to get him wet, I could do it without doing that. And then if I had someone else that came up and said, oh, you know, I want to get him wet, you could squeeze it and then you get all wet.
The water bottom?
No, top of the card. Now, the next thing is balloon in a vacuum. What was happening with the balloon in a vacuum? Why did it expand? Why did the balloon expand? Tell the person next to you.
Well, when you like have a balloon and like try to suck on it, like you've done that before. Like when you sit down and you make a bubble inside your mouth and you start sucking on it, it gets bigger.
All right, which one had a greater pressure, the balloon or the vacuum chamber? Which one of these was at a greater pressure, balloon or vacuum chamber? Vacuum is wrong. The balloon, greater pressure. The reason why is the pressure due to the air in the vacuum chamber went down because the air got pulled out. So there was less air, less molecules of air. This causes the balloon to expand. And then it contracts when you release the vacuum because the pressures equalize. What about the marshmallows? What was happening with the marshmallows? Similar thing, right? They expand. And then they shrink a little bit. Why do they shrink a little bit? Okay, there's some little pops going on. It's like a bunch of little balloons in here. The middle balloons didn't pop, just some of the outside ones popped. And then when you equilibrate it out, you got your little shriveled marshmallow. That tastes really good. So these are all changes. Now, last one is water in a vacuum. So we had a cup of water. Its temperature was at about 69 degrees. Was the water boiling? Was it bubbling? Yep, it was bubbling. It had liquid and gas in it. The definition of the boiling point is when there's liquid and gas present. So was it boiling? Yes. It was boiling. Was it 100 degrees? No. Not 100 degrees. It was boiling at about 69 degrees Celsius. So why was it boiling? Well, inside of the vacuum chamber, the pressure inside of the vacuum chamber was less. The pressure due to the water was when it was equal to the pressure inside. When the pressures were equal, this causes bubbles to form inside the water. When the pressure is equal to the water pressure, when these two are equal, this is when water boils. So if you want to stop water from boiling, all you have to do is increase the pressure. If you increase the pressure, that reduces water from getting to its boiling point. So if you increase the pressure, you can actually take water and heat it up to a higher temperature. It will go above 100 degrees Celsius. The problem is you also create a gaseous container that could explode because the pressure inside is so great than the pressure outside. So this is one way of cooking that is very quick and fast and efficient and can also explode your entire kitchen. Sometimes it's referred to as pressure cooking. You should never try to pressure cook without a pressure cooker because you'll get a pressure explosion. But this is why water can boil at room temperature. If you reduce the pressure, the water boils at a lower temperature. That's because of the pressure inside versus the water pressure. If they're equal, the water will boil. Now, we've looked at a lot of examples. How is pressure defined? The definition of pressure is it's the force applied over a specific area. So in your notes, some people like it F over A is pressure. It's not F equals MA. The F in the F equals F over A, the F does equal MA if you want to do some physics on it, but that's not the equation we're using. So pressure equals the force over a given area. Gas pressure is caused by gas molecules striking objects or the walls of a container. When they strike the walls of the container, these are called collisions. So pressure is proportional to collisions. Question? Mm-hmm. Interesting question.
Try it. I can cheese in my pockets.
Pull it out. its temperature will go down instead of up. So the melting of cheese is dependent on a heat change, not a pressure change. It might bubble, but it's not going to melt. So it will bubble. It will reach its boiling point, but it may not melt, which is yeah. Area. All right, next thing. All right, in the example shown today, gentlemen and others, and ladies. All right, so there are always two types of air pressure to consider. The air trapped in a container and the air from the outside of a container. Okay, the air that was outside of most of these containers was referred to by the word atmospheric pressure. This is the air pressure that is always present on Earth and as a result of air molecules colliding with the surface of objects on the planet. At sea level and 25 degrees Celsius, there is about 14.7 pounds per square inch of air pressure from the air around us. This is referred to as 1 atmosphere of pressure or 1 ATM. So to check in, I'd like you to turn to the person next to you and give evidence that gas molecules exert pressure on the walls of whatever container they are in. Any container you can think of, give evidence that gas molecules exert pressure on the walls of whatever container they are in, and then we are good to go for tomorrow. Homework is on the board. Quest is up. Will be up today. It will be due very soon, so get started on it immediately.
Wait for Quest?
Yep.
When's it due?
We do very soon.
Very soon.
It will be on the Quest assignment, so you'll know.
Alright.